Welcome back. This is lecture 5.1, where we're going to introduce the equation of state for a 1D solid, or a one-dimensional solid. Now, what I told you last time was that we needed to know our equation of state so that we could calculate a process between states, right? The process that allows us to transform from one state to another. We knew it for an ideal gas. We'd like it for a generic three-dimensional solid or liquid. But at the moment, we're going to start a little easier. We're going to do one-dimensional. Now, again, you can't really have a one-dimensional liquid. You can really only have a one-dimensional solid. And in fact, we're not even going to really do exactly a one-dimensional solid. Right? But you can remember why this is so important, because along our isobar and isochore, we didn't really need to know our equation of state. But along our isotherm, it was really important to know our equation of state. Okay, so our setup is going to be really just a rod of length L. And we're going to mainly focus on this one-dimensional property, although to be honest, it's going to have a cross-sectional area, right? And that's going to be important later. So this is going to be a fixed wall. And what that means is I have a one-dimensional rod or one-dimensional bar that's fixed at one end and free at the other. Okay? And now I want to know, how does it depend? Right? What does it depend on? Well, one of the things we know is that if I applied a force, I could squish this bar. We're going to ignore any bowing or flexing or stuff squeezing out the side like jello. We're going to assume it's stiff enough that it just changes in one dimension. So we could apply a force. This is also really a tension, but I'm gonna keep thinking about it as a force. But it could also vary with temperature, right? So if I change the temperature, this could expand or contract. Okay, so we're going to have a function L, my length, is going to depend on the temperature and the force applied to it. Okay, so the question is, let's start by fixing F. So let's start with a constant force. And imagine what happens when we change the temperature. So what I mean is, how much does the length change if I change the temperature? Okay, so I want to calculate a delta L. But I also know intuitively that if I had a really, really, really long bar and I changed the temperature, it would change more than if I had a really short bar. Right? So it's actually also going to depend on the length of the bar. Okay? Sorry, and what I really mean is the initial length of the bar. So L0. So this is L minus L0 over L0. Written in terms of our variables, this is going to be L as a function of T and F minus L as a function of T0 and F. So I'm going to be fixing F now, but I'm varying T. So this is L as a function of T0 and F. So if I had this function and I evaluated it at this fixed force or fixed tension, and then the initial temperatures, and then the final temperature, or as a function of temperature. Okay, so now we can actually proceed with our calculation. So the first way to think about this is really just noticing now that the length, delta L, is going to be proportional to L. That's what we said there. But the change in L is also going to be proportional to the change in temperature. So I can really just put those together and just say that delta L is going to be proportional to L delta T. And if I assume that the changes in temperature are small enough, I'm going to assume that this is linearly proportional. So let's just call it equal to, give it some constant of proportionality, delta, which I'm going to call alpha. So this is our constant of proportionality. Which is going to be called our coefficient of thermal expansion. Now, one thing to note is that of course, delta L, we really want to turn into a differential. So we're going to call this dL is equal to alpha L dt. Or another way to write it is to think about this alpha, this coefficient of thermal expansion, now being defined, so 3 equal sign, right, the being defined as 1 over L, partial T at constant F. Okay, so what do I mean by this partial derivative? So remember, this is a class where we have lots and lots of partial derivatives, and here I'm just pointing out like what we've done. We assumed that they were kind of just changes, right? Changes we know are like deltas. If we think about this limit of integration, taking small enough deltas, well, then that really can be a differential. But, you know, we really had F fixed the whole time. L really depended on T and F. So here I was only talking about the temperature dependence, so I really have to write this L as a partial derivative of T with fixed F. Okay? So our coefficient of thermal expansion is 1 over L dL, or partial L partial T at constant F. Okay, a few notes about alpha. So it's defined again for constant force or constant tension. And usually when you look it up, it's going to be at 0, right? 0 applied tension or applied force. It's going to depend on the material, right? So alpha depends on material. And alpha is temperature dependent. Also, alpha is usually positive. But not always. There are a few rare materials that have negative coefficients of thermal expansion. So I'm going to give you one number just for a calculation we're going to do in a few minutes. So the coefficient of thermal expansion around room temperature is 1.15. 1.1 times 10 to the 5, and the units are inverse Kelvin. All right? So you can see that we have length, and temperature. So their units are inverse Kelvin. So 1.1 times 10 to the 5 for steel. So we're going to use that as an example in class. So you can write that one down and use it in class. Okay, now I have a really nice graph that shows how alpha depends on temperature for a whole bunch of materials. It's taken from a book called Pobel. And I'm actually going to stop the video and I'll splice that in here and we'll discuss it. And then we'll start with lecture 5.2 on the next part of our equation of state for a one-dimensional solid, which is fixing the temperature and varying the force. So the first thing I want you to notice when we look at this graph of the relative linear coefficient of thermal expansion versus temperature for different materials is that it's the relative linear coefficient of expansion, delta L over L. So we already talked about that in class, how when the length gets longer, it's going to expand or contract more. So this is really a percentage here. So we've got a percent, and you can see that it's varying between almost negligible percentage, maybe 0.1% or 0.05% for some materials, all the way up to more than 2% for others. You can also see that almost all of these are negative, right? So as the temperature goes down, they contract, right? That's as you expect. And then you can see at the top, certain materials like, in particular, glass and Pyrex, tungsten, steel, these things, stainless steel, have very small coefficients of thermal expansion. So there's some very interesting ones. So there's this one, number one actually is both Invar and Pyrex. So Invar is a very special alloy of steel that's invariant, right? Actually, it's supposed to have the least thermal contraction. And there's actually another alloy that's not on the list, which is called Covar, and that's covariant. It actually contracts exactly as much as glass does. So let's see, you can see some other things. So ice actually is 15. It's got some interesting temperature dependence. You can see it doesn't go to 0, so it's going to go positive at some point. And so as also does mercury, right? So mercury are going to go have a little bit curious temperature dependence. But you can see some things that are plastics, like let's see, number 20, which is Teflon, actually contracts quite a bit. So that's something to be expected. Okay, and with that, we will end this lecture, and I'll see you next time.